I'm going to talk about, once again, the small section around the foundations and not so much the long sections between the foundations, and very much around the section of the cable that's not buried. So between the cable burial and leading into the foundations. So what I'm really looking at is the cable burial, the section that's not buried, over running mostly for the on the wind farms where the cable is in the very first wind parks that was not even scour protected, that was just on the seabed, and later was due to scouring, was actually protected with scour protections, as seen here on this first slide here with the two cable protection systems over the scour protection, and on the latest on the lower slide here on the right. Right, that's a system with the edge scouring on the outside. Most of those systems, the scour protection or the edge scour there is also seen on the. It's not just seen on monopiles. It's also seen on jackets. And here in one of the projects, this is the Sea Green project where we're using jackets, three-legged jackets, where the actual suction jackets were almost the same size as XXL monopiles. We were having, or some of the issues that we have with cable protection systems and the interfaces that some of the speakers today have raised, where the interface between the foundation and the seabed is not always very clear. I have here on the top left the interface that's typically a little bit unclear. It has been taught in a few of the later presentations this morning that the seabed interface is not always a very clear understanding, where many of the presentations that at least I have been part of in the approximately 50 projects, offshore wind projects I've been part of. This has been presented as almost, when I see the drawings of how we are going to install the cable systems, we're looking at a drawing where it's almost by millimeter accuracy where the cable is being buried into the seabed and what distances. And so we have, which those of us who have been in projects, it's of course impossible to arrange things with millimeters accuracy at below the water. And you then come offshore and you find out that the monopile is actually 3 meters out of range. We are actually, this afternoon, we are going to Holland's The Coasts project, and that's one of the projects where the scour protection was pre-arranged before the monopiles were installed. And on one of those locations, for example, the monopile was positioned 3 meters out of the locations where the scour protections were dropped. So you can imagine then when you come with the cable protection system, one side there's 3 meter longer distance for the plow to actually start, or not the plow, the trencher to actually start trenching the cable protections or the cable protection system into the seabed. So you have a longer distance on one side of the monopile than the other side. And of course, that's not being accounted for in the analysis that's being made before. So that's the kind of the thing that's a big difference between the analysis and the assumptions, models, and so that are made before the project and what we actually see. And then for the benefit for the long distance travelers in the room, from Aurora. They have made some very nice models. Unfortunately, they wouldn't allow me to do the videos, so I'm not going to hang up the presentation. I just have these two stills here. The nice thing with this, on the left-hand side with all the colors, which was what we believed in the 2020s, we believed that or 2010s, we believed that the constant current was the big problem that we were fighting for, what was causing the scouring around the foundations. And so I actually have met quite a few people in the offshore wind that believe that we actually did, when we set out the mid-mast and so in the first wind parks, that we could actually, the data we got when we put out the mid-mast, that was actually the mid-ocean data that we collected when we had the mid-mast out. That was what it was when we had built the wind park. So this was the conditions that was out there after we had built the wind park. And of course, when we then put up the foundations, the currents obviously were a little bit different because the currents now had to navigate the foundations on the seabed. And later, as we saw in the scouring around the scour protection, of course, also the scour protection. And on the left-hand side, you can see that the scour, the current has to navigate around the foundation, and obviously the current around the foundation is about 1.8 on the side of the foundation, and on the lee side, of course, almost Silsnada, and so there's an FU there. That's a filter unit. So that's the filter unit that Aurora showed us yesterday. So the FU is not something very specific. It's just a filter unit that we can't see in this picture. But that really isn't the big problem. The big problem is what we see on the other hand, on your right-hand side there, and that's a cyclic effect. It's really the waves that's the big problem. And it's the big problem because only in 2020s, 2022, when Ørsted found out that on a specific project in the North Sea, that they had a problem which later was becoming a kind of I think it was known as a kind of a tumbling effect of the cable protection systems that were used, that they basically became a deburring machine for the cables inside the rotating cable protection systems that basically or destroyed the cables in a couple of years in operation. The reason is that the waves are driving the currents at the seabed with water particle speeds that are 4 to 5 times higher velocities than, for example, the OrcaFlex program can actually predict. And therefore, what that really means is that if you were doing a CFD analysis with the correct analysis setup, you would end up finding that the actual stresses or the water currents that hits the cable protection system is 4 to 5 times faster, and therefore ends up with much stronger forces, and therefore the curvature and the stresses that is bending the cable protection system, and therefore the cable inside the cable protection system has a much higher stresses, is bent to a lower bending or a higher bending curve, lower bending diameter than is being predicted. And this is, of course, the reason why a lot of the cable protection systems are failing at a much higher rate than was predicted. So we have lots of analysts saying this is going to last with no problem for 30 or 40 years. but it failed after a few years, and in some cases, even within a year. So one of the more troubled fields, like, for example, Yunlin in Taiwan, where we had several cable failures even within a year. This is what it looks like inside the cable on the right-hand side of Yunlin. After 9 months, it is a cable, yes, and it looked like you've seen some of the other pictures. The armors is all gone. Look exactly the same on a specific, I'm not allowed to say the name, in the North Sea, English sector, certain Danish company, I'm not allowed to say the name. After 2 years and a couple of months, this is the other end of the cable that actually burned out, because the end that burned out when there was still 33 kV on it, obviously you can't dig it out after it burns out. It's of course just a melted. But this is the other end. This is what it looked like. After 6 more weeks, we can look into the conductor. This is what the cable protection system looks like. And you've seen the curve. A couple of the people here have shown us what the curve looks like in Orcaflex when, but that's just a still of the curve of the CPS curvature. What do we do about this? You don't have to tell me. But yes, we put a rock berm on it. And when we put a rock berm on it, we get the irons I put in. We stabilize the cable. That's what we do in industry. That's a gold standard in offshore wind at the moment. So what do we actually get out of this? We actually, by localizing the or by stopping the mobility at the seabed to stop this CPS and the cable from rolling out around on the seabed with this 17 tons of stones, rock on the seabed, this rock berm that we put over the CPS on the seabed. We just have the part of the CPS and cable from the rock berm on the seabed up to the aperture on the monopile or the J-tube, or if it's jacket, to move by the currents, and thereby, unfortunately, then you localize the movement of the cable between what is being pinned down under the 17 tons of rock, which is now probably with the specific gravity of 2.8 of the rock, something like 11 tons or something underwater. What's being pinned down under the rocks and what's being moved by the water. That's obviously just like putting the cable into a vise. You move part of the cable and you have part of the cable under the rocks and you start moving it. That's of course not going to last for 30 years. Nobody have done the analysis of that, and nobody can actually tell what and where is it exactly being held in that vise. Inside the CPS, it's not filled up with water, as the analysis tells. It's actually filled up with sediments. So that's a bit of the problem, of course. The analysis, I'm just going to put up a few things. AI is good for many things. And one of the things it may not be so good for is just one example here. People are thinking it's good to have these things with the soil spring models. And so I'm just having one example here of one VisiPro here saying, well, here you don't really have to think about this soil spring yourself, because we here have a model that will give you the soil spring yourself, so you can actually get this out. I believe it's a bad idea that you can actually just download this, because this is one of the big problems, that you can just get this soil spring model just by from a DNV model and say this you can just download and get into the model. Then you get even more of these Orcaflex models coming out with a prediction of, yeah, everything looks good because the computer says it's going to last for 30 or 40 years. You actually have to do an assessment of what is the seabed, not what is a program telling. VIV, is that a big problem? That's one thing I don't understand about VIV. Luckily, I'm not a hydro scientist or something, but when the CPS and cable is being moved around by the waves, like it is close to the CPS for these 10, 15 meters between the seabed and up to the foundation, it's being moved around by the waves with a typical wave period time of something between 10, 12 seconds up to when the very large waves comes in, close to something maybe 22, 23 seconds, something like that in Europe, where we have had the wind parks for a long time. I don't understand how we have a lot of focus on the VIV, because I believe it's been the waves that's been moving the CPS around. Maybe we have VIV, but I don't understand how we can verify that it's VIV that have caused the failure. I believe it's actually the mobility from the waves that have actually damaged the cables. I don't think we have been able to say, well, it's VIV, or can we even talk about it? I believe after we have straightened up the things and we have put down the rock berms on top of it, like we see here from mainland China in the Taiwanese Strait, where we have a 22-meter long free span. Maybe here we would have VIV. And then just a small thing before I go on to the thing why I believe a few things have been done. DNV have a few good things. They make this standard ST359 and the recommended practice 360. One of the things I believe that's been said very little about, I'm not going to say anything more about it, but I'm just going to say DNV has been a little bit smart, because they actually say that dynamic cables shall be designed to, so everywhere where the cables, they see some dynamics, DNV actually specify that you have to use this OS. It's there, you can see the copy of it. So you really have to look this. You cannot just rely on ST359 and RP360. I believe there was a missing link. And the reason why I believe there was a missing link was we needed something to basically fit over these things. And the reason why I believe that was that we needed something that could stabilize and anchor, give verified anchor strength, actually looking over and basically mitigate the unknown geotechnical issues close to the foundation. And that was the reason why I basically was thinking, couldn't we just take a bench stiffener and making a bench stiffener close to the seabed, basically giving the seabed a bench stiffener. And that's what I basically was thinking, couldn't we do that at the other end of the CPS? And that's what I basically did. So I was thinking, well, we can put a curvature control at the seabed and we can basically anchor it. So we put a few spikes into the seabed. We just make these spikes deep enough into the seabed that they are not being impacted by a mobile seabed. They're not being impacted by any changes. And so then we can actually control the changes. That's what we tried this out. I don't know if I can get the, I tried this out. Yeah, we can make it work. We tried it out. Unfortunately, I live in Norway, and in Norway, the weather doesn't always play with us. So unfortunately, we had minus 15 degrees centigrade and almost a meters of snow while we were testing the thing. So it looked like this. We tested this. I basically tried to do the same as API 17. So I've been running this to what basically is the same as a API where 50-year storm continuously over a year. So we accelerated it to a year. So it's been running for what is the equivalent of 365 days of continuous storms. We've done that a couple of times. We've been testing it and drilling it down to the seabed in Denmark. And we now are in a situation where we've modified it a bit so we can actually put it in where we can address it to where we have free spans, so we can both access it in areas where there are, we can basically fit it in where free spans have already been established, and we can actually establish it in seabed where scouring will happen, and we can establish it on scour protection. And as shown here, you can see it's floating above the thing. These Chinese looks like patterns there, Chinese hats almost. What else was I going to say? We are currently making tests where we are penetrating armor layers of scour up to 300 kilos armor stones, which is the largest armor gratings that are being used at the moment. And we are doing wet testing we are planning wet testing, wet installations. So that's underwater installation of this system with an ROV system before the summer this year. The wet installation is happening with screw piles. We use these screw piles. We were thinking about using DTH, as you see on the other side, but that's going to be a very fallback solution because we don't really want to use the casing. That takes a long time. So we hope that with our casing or with our screw pile solution, that we will actually facilitate the testing that we're running at the moment, which looks very promising, that we'll be able to do the screw pile you see on the right-hand side, that we'll be able to screw that to the armor rocks without the use of the DTH, as you see on the left-hand side. So we can screw the piles straight to there. So what we do there, we screw these into the seabed. So each of these piles that we screw to have an approximately anchoring strength that we get verified via a cloud service while we screw it in. So we get that verified as we screw it in during the installation with a minimum anchoring strength of 25 tons for each of the piles. So we get a nice as we go on the go. So you don't get it instantly, but you get it within a few seconds. You actually have the anchoring strength. I think I have to stop now. I think if you want some questions.
Okay, thank you very much. Just to make sure we have time to eat, let's do one question, if there is one. No? Last chance?